Hey, just a quick refresher on the hybrid orbital theory. So the hybrid orbital theory we talked about before, that's the sp, sp2, sp3 thing. So atomic orbitals in the same atom combine in order to form hybrids. And so atomic orbitals of different atoms, then they overlap, and so, a carbon would form 3 sps, and then it would overlap with maybe a hydrogen's s orbital, whatever it may be. What this helps us do then is match observed bond angles with the way we draw molecules. If they just overlapped their electrons as is, so they didn't morph into new hybrid orbitals, we wouldn't get the bond angles that we observe. Yeah, I hate to break it to you, but there's actually problems with this theory too. Not that it doesn't work, don't get me wrong, it works great for what it does, but it has limitations. One of the limitations is when we talk about hybrid orbitals, we're talking about individual atoms, but molecules aren't individual atoms anymore. It's atoms combined together to form one molecule. So instead of thinking about bonding as carbons bonded to hydrogen, we got to think of it as carbon and hydrogen, they're now an item, they're a thing. So if they're a thing, they no longer have the atomic orbitals, the 1s, 2s, 2p, 3p. They're now going to have molecular orbitals. What a great name for a theory. So it's the molecular orbital theory, sometimes called the MO theory, or if you want to really shorten it, you can just call it MOT. So what it does is it views a molecule as a whole instead of a collection of individual atoms. Really, methane, CH4, it's not carbon with 4 hydrogens, it's methane. It doesn't have the properties of carbon, it doesn't have the properties of hydrogen. It's not even a combination of the two, it's methane. So molecular orbital theory looks a lot like electron configurations. We still have all of the little individual guys, like you would have your 1s, and then you'd have your 2p's. It's going to look slightly different, but it's kind of that same idea. You've got the lines, and you put the electrons up and down inside each one, and there's rules for filling the orbitals, just like there is for atomics. So when we have two individual hydrogen atoms, those two individual hydrogen atoms are going to have their own atomic orbitals. And that's what we had talked about a lot, where it's got the 1s and 1s, and this guy would have 1 electron, and this guy would have 1 electron. However, once they join together, they no longer maintain their individual atomic orbitals. They're now a molecule, so they're going to have molecular orbitals. And so when those two combine, they're going to generate 2 molecular orbitals. So 2 atoms combining from 2 atomic orbitals will make 2 molecular orbitals. So the first one is called the sigma 1s bonding orbital. And then the other one is sigma star 1s, and it is an anti-bonding orbital. And so with an anti-bonding orbital, they're not really bonding, because you can see the electron density spends most of its time away from the center where the bonding occurs. With a bonding orbital, though, you can see the electron density is put there between the nuclei. So as a result, this is going to be a lot more stable than this is, because down here you have both of those nuclei kind of reining in and controlling all of these electrons, so the effective nuclear charge idea. Whereas up here you have this proton in charge of all of those guys, and that proton in charge of all those guys, and since they're actually kind of pushed out to the side, it's going to require a little bit more energy. And so this is actually drawn according to the energy scale. So remember, atoms are lazy, they want to get to the lowest energy state possible, and so the sigma 1s bonding, that is less energy than the original 1s atomic orbitals. And so this would be the lowest, this would be in the middle, and then the anti-bonding, so the sigma star 1s, is going to have more energy or require more energy than the original 1s atomic orbital. So these guys aren't going to automatically go up to the anti-bonding one, because that's more energy. Off-bow principle says that they would start out down here. So here's how we would draw that. Just like before, we represent each orbital with a little line. Okay, but now these are the atomic orbitals, so here's one hydrogen atom, here's the other hydrogen atom. They each have their own 1s orbitals. And then we can see on our energy scale right here, so energy increases as we go up. Down here is our sigma bonding orbital, and up here is our sigma star anti-bonding orbital. Both of those are generated when these two combine, but electrons, because they're lazy, off-bow principle says they're going to automatically go down to the lower energy one. So this electron would come down here, this one would flip directions and join it down there. So now they are bonded in the sigma 1s orbital. Let's imagine for a second that instead of H2, this is helium-2, so He2. So this would be one helium atom, which means that it would also have a down electron, and this would be the other one that would also have a down electron. So each orbital can only hold 2 electrons, just like in the atomic orbitals, same thing with molecular orbitals. So the first 2 electrons are going to come down here, and then the second 2 electrons are going to have to come up here, so they're going to go to a higher energy state into the anti-bonding region. All right, this actually generates a more unstable molecule because we have 2 electrons in the bonding region, but we also have 2 electrons in the anti-bonding region. Molecules, atoms, prefer to have more electrons in the bonding regions than they do in the anti-bonding regions. And so in this case, when it's even, that's not a happy case. And this explains why hydrogen or helium does not bond. So you don't ever see He2 because it generates anti-bonding molecular orbitals that disrupt kind of the stability, and so it would prefer just to be on its own. All right, here is the MOT diagram for oxygen, O2. Now, there's a lot of stuff going on here, so I'm going to try and talk our ways through it. Might get a little bit confusing, might need to pause and rewind the video. You might need to ask some questions in class when you guys see me again. But I'll try and do my best. So what we see in the center region here, this is the molecular orbital diagram for O2. On the outsides, these are the individual atomic orbitals for each oxygen atom before it's bonded to anything. So this is when they're single, this is when they're together. Now, first off, there is a mistake on here. The atomic orbitals should only have 2p4. And so what we've got here then is up, 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 and then down, and up, 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 and then down. That's the way that oxygen should be. So when they fill the molecular orbitals, it's just like it is with atomic orbitals. They start at the lowest energy level, they'll go up, 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 down, 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 whatever they need to, and they'll work their ways up. So a couple things for you to notice. One thing is that we now have a pi molecular orbital, just like atomic orbitals have s, p, d, and f. The molecular orbitals are going to have sigmas and pi's as well. So the 2s electrons are going to start off in the sigma 2s, and the first 2 electrons are going to come in and fill in that lower energy level. So notice how they move down in energy to go to the sigma, that's the bonding region, and the next 2 electrons have to go up in energy to get to the sigma star, the anti-bonding region. So they are increasing in energy. Now, that increase in energy, that wouldn't be stable if it stopped there. But since our next 2 electrons are reducing their amount of energy by a vast amount, so look at the difference in energy between that point and that point. That makes up for the little bit of energy those electrons have to expel to fill in the sigma star. And then we keep in filling in that molecular orbital diagram. So you notice that this the bonding regions, so the pi 2p and the sigma 2p, the electrons that enter those always go down in energy. In order to enter the anti-bonding regions, though, the electrons have to move up in energy. So with this particular molecular orbital, though, you'll notice that the electrons, for the most part, move down in energy. The few that had to move up, they were canceled out by the more that got to go down in energy. So overall, this structure has less energy than these 2 individual structures. So oxygen is happy bonded, and it relieves some of its energy. It can be lazier that way. Also, from this MOT diagram, you can see that oxygen gas is paramagnetic. It has these 2 unshared molecular orbitals. So just like it is with individual atoms, we would say that oxygen is paramagnetic. It would be attracted to a magnetic field due to these unfilled orbital regions, or unpaired electrons. So here is the MOT diagram for hydrogen fluoride. Something you're going to see in here is a non-bonding orbital. So a non-bonding orbital that's different than a bonding or an anti-bonding. These guys, they're essentially neutral. They don't attribute to instability or stability. They're actually at the same energy level as they were to begin with. And what it is in hydrogen fluoride is those would then represent your lone pairs. So if you imagine the Lewis structure, it's going to have 3 lone pairs around the fluorine. So according to the MOT diagram, 2 of those electrons are going to come from the 2s, and then 2 of them are going to come, or the other 4 are going to come from the 2p. And then you would have 2 electrons in the bonding sigma sp region. And the sp would be from the sp hybridized orbital. Okay, here's just a breakdown of the different molecular orbitals, so the bonding, anti-bonding, and non-bonding orbitals. So while you guys are reading this then, something else that the MOT theory, or the MO theory, helps us understand is how we get different colors from different molecules as well. So we talked about before with spectroscopy that we generate different colors because different atoms, their electrons hop up and down. With these bonding orbitals then, we can see how the electrons would jump from one energy, so they might jump up to the anti-bonding or to a 2 sigma or a 2 pi, and they fall back down, they generate different colors. And so it helps us explain then how we can get colors from molecules as well as we do from atoms.